processing supercapacitor material and component. We know the supercapacitor is another type of energy storage device like a lithium-ion battery, and has been used. There's more and more use of a supercapacitor combined with the lithium-ion battery for electrical vehicle, for example. So in this presentation, first I'd like to describe a little bit on the principal application and challenge of the supercapacitor in case you are not familiar with this device. And then I will give 3 examples to demonstrate that we can use laser to process in material and component for this supercapacitor device. The first example I want to give is use laser photochemical and photothermal reduction process to convert the graphite oxide to graphene and use graphene as active electrode material for supercapacitor. The second example I want to show you, we can use a laser to deposit thin film of pure phase, pure oxidation state of manganese oxide. We know manganese oxide is also a very interesting material used in supercapacitor due to its pseudo-capacitance property. So manganese oxide has very different oxidation state, and we want to prove what kinds of oxidation state will perform the best. So by deposit thin film of very pure phase and pure oxidation state of compound, we're able to compare the manganese oxide of different oxidation state and compare their supercapacitor behaviors. Then the last example I want to give is just how we can use laser to process a current collector for supercapacitor. The current collector is used to collecting the charge from the active material in the supercapacitor. And the interface between the active material and current collector is very, very important. The objective is to reduce the interfacial resistance between the current collector and active material, so the supercapacitor device can deliver charge in a much quicker way. In another term, it had higher power density. And I will give my conclusion. So this give a simple structure of a supercapacitor. So basically, you have a 2 current collector, which is thin foil of aluminum, and you have active material. Active material consists of, for example, activated carbon mixed with some conducting carbon like kitchen brass, and you use a binder like a PTFE binder to bind them together, and you make it extend along a membrane. And then in the middle, you have a separate. Separate basically is a polymer film, has porosity and very, very thin, typically 5 micron to 10 micron. So this separate basically separate the electrical contact between the 2 electrodes, but allow the ion to transport between the anode and cathode. In this example here, the anode and cathode are used as identical material, so it's called a symmetry supercapacitor. So basically, you have this 5 layer, you squeeze them together, and fold them, and put a 2 electrical contact and put into a container where you inject the electrolyte to form the device. So you look at the detailed structure, actually, those activated carbon has very large surface area. And typically, per gram of activated carbon, you consider thousands of meter square surface area. So instead of storing charge inside the material, the supercapacitor storage charge only on the surface of the material. So because it's stored only on the surface of the material, it can display the charge very quickly. So it's a very good high power device instead of energy device, which is like supercapacitor, like a battery where the charge is stored inside the material. So it takes time from charging from inside, go to the surface and then discharge. So supercapacitor can discharge charge much quicker than battery, for example, like a lithium-ion battery. The important parameter for supercapacitor is the specific capacitance, which tells you how much surface area you can use to store charge, and the voltage between the 2 electrodes. So, for example, an aqueous electrolyte you use is about 1 volt. If we use organic electrolyte, then it goes up to 2.7 volt. And square root of 2.75 times, this means use organic electrolyte, you can store much more energy compared with aqueous electrolyte. And the power, how much quicker the energy can distribute, is depend on the voltage and also the equivalent shear resistance. Basically, is the resistance between all the components. So between the current collector, active material, and active material separator, active material, another current conductor. So in order to reduce the resistance, you would able to achieve very high power. So this is very now called regenerative product. Basically compare all kinds of energy device. So for example, lithium-ion battery, you have a pretty high energy density. This axis give you a specific energy density, told you what's the weight, like a 1 kilogram, how much energy you can storage. So compared with lithium-ion battery, supercapacitor has much lower energy density, but compared with a typical electrolytic capacitor, supercapacitor has higher energy. But compared with lithium-ion battery, supercapacitor much higher power density. So this line here tell you how quickly the energy can be dissipated. For example, in here you have a 10 watt per kilogram of energy, and supercapacitor it can dissipate in 36 seconds. But in same thing in battery, you can see you typically dissipate energy in much slower way, in hour typically. So why you need a supercapacitor? Supercapacitor in the electrical vehicle, actually you could combine with a battery together. So supercapacitor can provide a peak power. When you start a car, you need a lot of current. So if you want to only use a battery, then you need a huge size of battery. But you combine supercapacitor and battery, then supercapacitor can provide the instant power that need, and then battery can provide the long distance driving. And also you can recover energy. Put on the brake here, you can put a supercapacitor. When you slow down the car, the energy, transitional energy can convert to chemical energy storage in a supercapacitor. So that is a benefit of combined supercapacitor and battery. So what's the challenge of supercapacitor? Basically, there's two main challenges. You had to improve the performance and you had to reduce the cost. In terms of improve the performance, you had to increase the energy output. So how can you increase the energy output? First, you increase the surface area of this active material, the large surface area that you can store in more charges. So then people talking about, just use activate carbon, you can use a graphene because graphene has much larger surface area than activate carbon. And also you can store the charge not just on the surface, but also on subsurface. So for example, pseudo-capacitor material are conducting polymer. So these types of supercapacitor is a little bit mixed between the supercapacitor and battery. But in the case of battery, the charge is stored inside, really inside the material. But in this case, a pseudo-capacitor charge only store surface and subsurface. So this charge can be released also very quickly. So it behaves almost like a supercapacitor. So it's called like pseudo-capacitor. The other thing is you can increase the conductivity. Conductivity of all components contribute how quickly power can be, how quickly energy can discharge this mean power. So increase the conductivity of active material, reduce the interface resistance between the current conductor and active material, and use smaller size of separate or more pole separate. But separate, if too small, then it causes danger of short circuit. So there's a limitation there. So then we talk about why graphene, because there's so many research on graphene now, and why we use graphene for supercapacitor application. In theory, graphene is a planetary structure. So ion can easily stay on the surface and can come up very quickly. It's not like active carbon, there's a channel and ion had to take time to diffuse inside the material and then coming up. But this is just a kind of like piece of paper, charge set on the surface and can come and go very quickly. Second, you have theoretical surface area, which is over 2,675 meters ground, which is way higher, much higher than commercial use activated carbon. Therefore, allow storing more charge. And graphene itself is also a very good electronic conductor. But what is the challenge of graphene? Because when graphene, you cannot be, most of the time it's not stand along a sheet of graphene. They have a tendency to stuck together by van der Waals force. So when it's stuck together, ions cannot go in between the sheets. So then there's a resistance for ion to go in, and amounts of ion really can go into occupied all the surface graphene. So this is a challenge. So then we talk about why we use laser. And laser is very clean process. It's environmental friendly process. For example, you want to reduce graphite oxide to graphene, you use all kinds of chemical reduction agent that can cause environment issue. But we can use a photothermal on photochemical mechanism of a laser to basically reduce the graphite oxide to form a graphene. And graphene is used as active material for supercapacitor. And also we can, for example, we can deposit graphite oxide films and on the substrate, and you use a focus laser beam to machine the film to form a thin film device. For example, graphene sensor, graphene thin film supercapacitor, etc. And again, I said we don't use chemical, and it's poisonally material-free alternative to the chemical method. So this is the process that we use. So basically, you get buy a commercial graphite, and you use a hammer method to form a graphite oxide solution, and it's dissolved in water, and then you can basically irradiate by laser with graphite oxide solution. So is it a solution, and you just irradiate with laser, and basically laser use photochemical method as a process to reduce the graphite oxide to graphene. And then you put this graphene solution and coat it on a metal current collector to form a graphene active electrode. So basically, in this example, we use a gold film and then coated graphenes. And you can see the graphite oxide, the graphene is a very large sheet. After irradiated by laser, it becomes a very small size of sheet, but it's very porous. So that allows iron to go in and out easily. So we want to prove that the graphite oxide it is indeed reduced by laser, and we do an X-ray diffraction. And this is just a graphite oxide solution. You can see a very clear peak which due to 0011 of graphite oxide. And after irradiated with laser at different time, different energy, you can see this peak is disappear. And you also see a band here begin to appear, which means this band is due to graphite. So this multiple sheet of graphene is beginning to stack together. And you can see the XEM topography. You can see the graphite oxide, you have a large sheet. After irradiated by laser, it becomes a porous, a small sheet. And then we do the XPX to confirm that we indeed also confirm indeed we did reduce graphite oxide to graphene. And this is just a graphite oxide peak, and this is a graphene peak. You can see this carbon oxygen functional group was disappear in the graphene, and carbon double bond become more percentage become increased. So this indicates that the graphite oxide was really reduced to graphene by laser process. And then we do the testing. So we coat the graphene on gold electrode, and then we assemble in this 5-layer system as I explained, and then inject electrolyte, use a spring to push the pressure on those 5 electrodes to improve the contact reduce the contact resistance, and you test in organic electrolyte and inorganic electrolyte and inorganic electrolyte. So the first thing we measure the special capacitance as function of electrode. So basically this told you when you apply the electrode, increase the voltage to the device, then you have current. If the current is constant, this means that the current is very easy to go in a constant way. So there's no resistance for the current to go into the device. If you see a peak like that, in the case of battery, this means, okay, the iron had to be overcome some resistance in order to go into the bottom of the material. So these kinds of rectangle symmetry shape indicate that charge is indeed stored on the surface, and it can store and discharge very quickly. And then you can calculate the special capacitance because the energy is proportional to the special capacitance. That special capacitance tell you how much surface allow you to store a charge and how much charge you can store it. So you can use the slope from this charge discharge curve and you can calculate. And we determined that the graphene reduced by laser has 141 farad per grams of specific capacitance. And from a tiny potential drop here, you can calculate the total resistance of the device, which we was find to be 1.6 ohm. Or another word, we convert to the area, then there's this is the value we obtain here. And then you can compare the special capacitance of graphene and graphite oxide. You can see graphite oxide almost cannot store charge. It's very, very low. It's only 0.6 farad per gram. But graphene, you can see increase significantly. And also you can see there's a decrease of special capacitance as function of scan rate. So this scan rate is how fast the charge go in and out. And when you scan very quickly, this means charge do not have, charge had to overcome some resistance in order to access all the surface. So this means we indeed have some resistance on the device because you cannot reach infinity here. So basically, if you, this is almost a straight line, this means charge, it has no resistance, charge can go in and out, no problem. And we also compare the graphene in organic, organic electrolyte and in organic electrolyte. You can see in organic electrolyte, basically aqueous electrolyte, you have higher specific capacitance than in organic electrolyte, because organic electrolyte, you had to use some salt which has a larger size than the aqueous electrolyte, which is proton and sodium, and so those are much small size of ion. So those ion can easily go in and out and occupy more surface than those organic electrolyte which has larger size. So in this part, we summarize that laser reduced process is very promising for produce graphene because it's excellent flexibility and capable to control the microstructure. Now we want to go to the second example, is that we can produce manganese oxide by pulsar-laser deposition process. So basically, you use a manganese oxide target here. You control the temperature, you control the oxygen pressure, then you were able to produce different oxidation state of manganese oxide, and then you put it into supercapacitor to measure their performance. So this gave an example at different temperature, different oxygen pressure. It was able to produce 3 different phases. C1 is crystalline M203, and C2 is crystalline M304, and A1 is amorphous MO2. Actually, we proved by other method that is amorphous MO2. XRT, you cannot tell it's amorphous. When it's amorphous, you cannot tell it's crystal structure. So then we compare the performance of 3 different phases. You can see and we do the special current as function of voltage here. You can see the crystalline M203 perform the best, and the crystalline M304 actually almost no much activity. And also we can plot the specific capacitance as function scan rate, see how quickly the charge can go in and out. Again, the C1 crystalline M203 perform the best compared with the other 2 phases. So the third example I want to give is how can we use laser to machine the current collector? So basically in the supercapacitor, you look at, remember when on the first 2 slides, I explained that you use the aluminum foil. And aluminum foil is very, very thin. It's only like a 5, 10, 20 micron thick. And most of the time, aluminum is very easy to oxidize in just exposed area where an oxide forming on the surface. But this oxide is very thin. It's in a range of few nanometer, 2 nanometer, or less than 2 nanometer. So when aluminum oxide is so thin, I mean, charge can still transport through this oxide layer by a tiny effect. But if you put into the energy store device and do the charge discharge for a long time, this aluminum oxide layer building up. So once it reaches certain thickness, then the resistance between the active material and the current collector become so big, then the power output of the device will be decreased. So by using laser process, we can create very, very large surface area, which we can increase the contact between the active material, which is graphene or activated carbon, to the current collector. So charge can be easily to transpose through it. And also when you have flux surface, the electrolyte can very easily go into due to this capacitive effect. So by doing this here, you can basically block in some of the electrolyte actually go into here. So then we compare the performance of the untreated alumina, and you can see the capacitance decrease very quickly when you want to increase the charge-discharge rate. But this curve is for pure gold. Gold, there's no surface pure, there's no any oxide on the gold. So gold is ideal conductor for this supercapacitor device, but gold is too expensive. And this one is a commercial one, it's the best commercial one. They use a carbon coated to protect aluminum from oxidation and as one surface oxidation. And this is what our laser treated one. And we can see that we are comparable to the best commercial device. And most recent what we did is not just we do the laser machining, we also put a coating by laser process. And we find out we achieve almost similar like perform as a goal, and we just submitted results recently. And so in summary, we can say that laser process can prepare very phase of magnetic oxide having different specific capacity. Laser process can capable control the composition, microstructure, and phase of various material. And laser surface treatment can significantly enhance electronic conductivity and the contact area and conduction between the current active material. So overall conclusion is that laser has a great potential for process material and component for energy device. So thank you, and I'm